We can use the finite difference for higher derivatives as well. If you remember, in the previous slides we showed that we can use this for the first derivative, but now we will check how to use it for the higher derivatives. First, we will just show the second derivative approximations, but this can be extended to the higher derivatives as well. So for that, we will use the Taylor series again, and we will use it for the step size of 2h. So that means f xi plus 2. We will just write the Taylor series for this, and we will write this in terms of f xi. This way we will have a step size of 2h. Because it's from I plus 2 to I. And if we write it down, f xi plus 2 is equivalent to f xi plus f prime xi and 2h plus the further terms, the second derivative for instance, xi divided by 2 factorial, again 2h, the square of 2h, and it goes like this to the infinity. And after making this, we want to multiply the Taylor series, forward Taylor series, by 2, and we will subtract it from this Taylor series with the step size 2h. So in other words, let's write it down. Multiply forward Taylor series, for just step size of h for this one, h step size. That means for f xi plus 1. We will multiply this by 2 and subtract it from the Taylor series of f xi plus 2. Let's do that. We will simply make f xi plus 2 minus 2 times f xi plus 1. And if we do this, this is simply 2 times. Let's do this way, not 2 times. First, the step size of 2h. So f xi plus f prime xi 2h, and goes this way, minus 2 times f xi plus f prime xi, but this time h. So this is f xi plus 1, the first terms. These are f xi plus 2. And if we subtract these, the result is minus f xi, because it is 2 minus f xi, and f xi difference is just f xi minus, and plus f2 primes xi h square, because these cancel out. Here 2h f prime, here also 2 times f xi h. But for the second term, or this one, the addition of the power will result in having the f double prime, or the second derivative, and it goes this way. So for the higher terms, we can keep higher terms in here, but for the second derivative, we want to just truncate from here. Truncate and isolate f second derivative, isolating f double prime xi gives us, so on the left hand side we had these, and we will just move this to this side and divide by h square, which makes it f xi plus 2 minus 2 f xi plus 1 plus f xi divided by h square. Of course, we will have a truncation error of OH. And we had this, and for the second forward difference, we will use this one. We can just say that this is second forward difference approximation to estimate the second derivative, second forward difference. And we can use a similar idea to have the second backward difference. And the result of it is simply, again, f double prime xi, but this time, because it's backward, we will simply have the backward difference approach. In other words, you can see the forward is I plus 2, I plus 1, I. In backward, it's I minus 1, and I plus I minus 2. So f xi is the largest, minus 2 times f xi minus 1, it's going backward, plus f xi minus 2. Again, this is h square, but the error is OH. And center difference is again simply the difference of the forward and backward difference estimations, and it gives us f double prime xi is equivalent to, this time we have I plus 1 and I minus 1 actually. Again, f xi plus 1 minus 2f xi plus f xi minus 1 divided by h square, and again the result is, the error is on the second power. We can write this in another way. You can see here that we have f xi plus 1 minus 2 times f xi. So one of the f xi can be grouped with this, and one of it can be grouped with this, and the right side becomes the backward and left side becomes the forward difference of the first derivatives. So then this second derivative, centered derivative, can be written as the difference of the first derivatives for forward and backward estimations. So let's write, this is actually, so this is second 2, and this second center difference is also difference of the two first divided differences. What we mean is that it is simply f xi, of course the second derivative, is equivalent to f xi plus 1 minus f xi divided by h minus f xi minus f xi minus 1 divided by h, and these two are divided by h, at the bottom you can see it's just this is the forward difference of first derivative, and this is the backward difference of first derivative. And by subtracting these, we will have the centered difference for the second derivative, which is a good approximation by using only the first derivatives and the differences of them. So we can use this for the second derivative estimations, and for further higher derivatives we can have similar formulations, and you can basically derive them in a similar manner.